plant model from a previous exercise, we will build a compensator that achieves 100% of the set point in one step without overshoot or oscillation. Impossible, you say. Normally, yes, but we can do this under restricted conditions. Let's build the compensator now, specifying linear output and 100% in one step. Copy-paste the coefficients from the data window into the spreadsheet. We are adding the restriction that the plant input can't be negative and it will not exceed 1 over the plant gain. This gives us a plant output in the range of 0 to 1. As we can see, we do indeed achieve 100% in one step. But the first plant command is about 800% of maximum, and the second plant command is about 500% below zero. Obviously, this is not realistic, but here's where we're going with this. Notice how the compensator gives an initial big push in the positive direction and then recoils in the negative direction and then settles at 1 over the plant gain as expected. Here's the initial big push, the recoil, and settling at 1 over the plant gain. The idea is to deliberately operate the plant at its midpoint and then allow small step changes in the set point that keep the plant input within bounds. Here we see the same system now operating around its midpoint of 0.50. Initially, we used a maximum set point change of 0.05. Notice that at every step change at the set point, there is a significant disturbance at the plant input. These spikes here. We are attempting to keep all of these disturbances within bounds, and we've achieved that goal. Now let's increase the maximum allowed set point step change and see how far we can go while still remaining in bounds. .0619 is as far as we can go. This translates to a step range of about 12%, or midpoint plus or minus about 6%. So using this plant, this compensator, and these set point restrictions, we are able to get the plant on set point in the next step. This is an interesting result, and it has the following implications. If you extend the capabilities of the plant beyond the nominal operating range, you can get very aggressive with the compensation, as long as you restrict the maximum set point step range. Now suppose you might be satisfied with slightly less performance, say 90% in 2 steps instead of 100% in 1 step. Let's build another compensator with exponential output and 90% in 2 steps. We'll copy-paste the coefficients from the data window into the spreadsheet. First, let's use the same input restrictions for both systems so we can toggle back and forth between the plots for comparison. Okay, they're both set to the same maximum set point change, and we can toggle back and forth between them here. You can see the sharp edges in the first plot, right there. And you can see the rounded edges in the second plot. Little rounding here, 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 and here. Let's see how far we can push the second system. 0.0906 is as far as we can go. This translates to a step range of about 18%, or midpoint plus or minus about 9%. Now let's use the maximum input restrictions for both systems and then toggle back and forth between the plots again, this time focusing on the plant input. Here's the plant input here, and we'll toggle back and forth a few times and you can see. The disturbances in the plant input on the second plot are a little less severe. Let's build another compensator with exponential output and 90% in 5 steps. We'll copy-paste the coefficients from the data window into the spreadsheet. Here we see more rounding on the edges, and the plant input disturbances are less. Here's the rounding and the disturbances. Well, we had fun exploring compensators with limited set point range, operating around the midpoint of plant output. Admittedly, this is pretty extreme, but it does show some interesting possibilities. This concludes today's video. Thanks for watching.